Hello, everyone, and welcome to ITW2022. Our paper is titled Code for Preventing Zero at Partially Defective Memory Positions, and this is a joint work with KJ Chan from the Singapore Institute of Technology and TUM Asia and the Technical University of München. Okay, so the partially defective memory cell has been introduced by Vakhtarza and Yaqoubi in 2016. And actually, the coding for memory with defect back to 1970s, but we took our references because consider error correction and defect masking code in Haggard in 1983, also Vakhtarza Yaqoubi in 2016, and our work in 2019. So this is our main three references here, and yeah. So the assumption in 3, which is our work in 2001, code construction in consider a scenario of Q level memory cell in which U cells are stuck or partially stuck. Here we call it or defect, partial defect at a level 1. And this means when it's stuck at 1 means the zero value is forbidden. And what is zero values here? It's from practical importance, because zero value means here we are going to the arising state, and we would like to avoid to arise the entire cell, rather just increasing the level. So these constructions in 3 are formed under the supposition that when random error occur in the partially defective cell, they coincides to the partially defective constraints. Assume we have some psi position representing the U error position and some phi position representing the partially defective position, and for any I equal j in the set, and from n set, and n is the memory cells and also the code length later. So for n cells, the assumption in this work was for any code word at position I, the partially defective position, plus the error vector at this position as well, which is j, and j equal I here, is not 0. And this is just an assumption. So this is an idealized assumption. So in the problem, for example, since the calculations are done in the finite field FEQ and CI and EJ in FEQ, we could end up with CI plus EJ equals 0. And this is why, because, for example, if we take CI equal Q minus 1 and coincidentally that EJ equal 1, then CI plus EJ mod Q equals 0. And this is not allowed for partial defective memory cells. So the overlapping happens in the area above the stack level cell. So we call a stack or partial defect level here S, namely Q minus S, as you can see the orange here, for example. So the flipping from 1 to 2 or 2 to 1 is allowed because we are not going to the arising status of this memory. So we just increase the level here. But flipping from 1 to 0 or 2 to 0 not allowed, and this is here happening by the effect of the influence of the the error vector E here at j position and j equal I. Okay, so our goal, we want to ensure that the partially defective constraints always preserved concerning the influence of potential errors. And in this paper, our contribution is we show that the probability that CI plus EJ equals 0 is not trivial. So we cannot just avoid it or just assume that's always the case. Then we modify the construction in 3 to ensure that CI plus EJ is not 0. So we fulfill the constraint. We can deal with least masked Q cells than the construction in 3, and this is actually cost us. However, it is more realistic regarding physical memory with a partial defect that also suffer from random errors. So our work preserved the required indices as achieved by 2 and 3. So the probability of overlapping position is given by proposition 1, and it's like in 1. And to prove that we have this as a non-trivial, we will show the proof as the following. Okay, So assume there is a P given UT for N, the probability that phi intersect with psi is not an empty set. And we know that phi has a size U and psi has size T, and such that both of them at least or equal N. So the proof follow the Binjon-Hall principle. So assume we have boxes, and each box N boxes, and this is an empty boxes, and we would like to put U items. So we start to filling the N boxes with the U item, and the left to N minus U item will be the boxes that, for example, for any new item T, the probability that we occupy the at most N minus U left boxes is given by 2. So after that, after filling the N minus U by T, for sure there will be an overlapping, and by the union bound of the probabilities of the overlapping will be 1 minus B T given N minus U empty boxes, which is the conclude our proof. So N1, as you can see. Okay, so this is the probability of zero occurrence in an overlapped position, which is given in 4. And here we will prove this. So let BCIEJ given Q be the probability of a pair of CIEJ satisfying this condition, which is equal to 0 value. Okay, so when it's equal to, is not always giving 0 value when they are overlapping. So there are Q squared total combination of a pair of choices of CIEJ and CI from 0 up to Q minus 1, and EJ also from 0 Q minus 1. So choose any of them. There are exactly Q choices such that this CI plus EJ overlapping mod Q equals 0. So the probability that BCIEJ given Q is a Q over Q squared. Okay, so this is independent of the probability in the proposition 1, which is the overlapping happen with the probability PUT given N. So as both events PCIEJQ and PUTN are independent, then the probability just the multiplication between, and this kind of showing here with the blue one and the green one, and the probability that the overlapping position gives a 0 value as given in the underneath here, which is in 4, the multiplication between the probability in from proposition 1 and the blue one here. Okay, so and this proof our proposition 2 here. Now it's non-trivial, so because this is a probability if U and T plus T are greater than N, then the probability in proposition 1 always 1, and which means here when there is an overlapping always, then there is the higher probability that this overlap lead to 0 value. So for example, for Q equal 3, it's 1/3, and for Q equal 4, which is always for practical importance in MLC, flash memory is 1/4, okay? So now we come to the main contribution in our paper, which is a modification of a construction given in a tree. And we take algorithm 1 from the previous work, and we call it here, recall it here again, and we modified step 2 and step 3 such that we can guarantee that when error occur in the partially defective position, the outcome will not lead to 0 value. And this is by modifying the condition on the augmented message vector omega here. So if we call algorithm 1, we have it here. So we modify this step, and the other one, this is omega, which is sum m multiplied by g1. If we go back to this, so this is our generator matrix, has some g1 for error correction capability, and g0, which is the all one vector here, okay? So the output vector will be something from an all position in FQN except the 0 Q minus 1 at the CI position, okay? Okay, so the decoding does not change here. We follow exactly the same decoding from 3, so given here in this paper. And yes, so the proof is the following: for error vector from 0 and 1, and we assume here that this is our error vector, and it's extendable, and we will give a remark on this. And the 0 and 0 are not permitted in the partially defective position, so this condition should be fulfilled. So because U is a conditional Q minus 1 over 2 round down, then, so that we have some gamma, which is Q minus 1 values, and there is elements VB in FQ such that for all I, some index VB in gamma, B in gamma, such that the value of omega I is not this VV value. Okay, so there is some elements in FQ that are not equal omega I. And we just show that for index VB, in gamma, there's at least a pair or consecutive VB, which is some value of B in this position in gamma. In FQ, there exists another value, which is a consecutive, just a VB plus 1. Okay, the encoder choose this value and obtain, and this is always fulfill the condition here. Okay, so omega minus this value, and we will fulfill the condition following the algorithm one for sure. And because omega I is not equal VB, this condition given in the second B, so VI minus VB is not also 1, because following some math here. And also, since this given also V minus is not 0 as well, then this value should be will not be 0 or Q minus 1. So it's always some FQ from FQ, but except these two values. Then we satisfy the condition here, and if we add 0 or 1, which is the error value, so will not be 0 anymore. And yes, this is satisfied, and we fulfill the condition. The as C is in FQ, for some coordinate in a partial defect position, not 0 or Q minus 1, is still a code word actually in code C. So the decoder use Y by using algorithm 2, and the correct T error return the message here. Okay, so corollary 1, we could do better here or more in terms of more masked cells, so we can achieve U least or equal Q minus 2, which is higher than the construction 1, which is Q minus 1 over 2 round down. If and only if at least a pair or consecutive element VB for V necessary exists. And this is not very hard to show. So let U up to this value, Q minus partial defect at one cell. So there must be at least 2 choices of VB, not necessarily here consecutive. So if this value of VB plus 1 is a VB plus 1, due to the random augmented message vector, then the encoder can mask up to this value, partial defect cell following construction 1. So this is obvious. Now, also we can follow the probabilistic masking, can mask up to U least or equal N minus 1, and this is because the randomly chosen message vector. So we have this probability of masking. This is a probabilistic method, so we depends on it when we have a probability that this message fulfills some condition. Okay, so for example, we know that the size of phi equal U, and we require 2 values of FQ must be excluded to satisfy this condition. We just exclude 2 values. However, these 2 values not necessarily to be consecutive. So we have, this is from the inclusion exclusion principle, such that we will have how many vector that exclude 2 field of an element, and then the 2 values are not necessarily consecutive. Now we need to find the probability that this is these 2 values are consecutive. So we calculate Q chose 2, how many pairs, and that are subject to commutative property, and there are exactly Q set have 2 consecutive entries VB plus 1. Probability to have a consecutive VB plus 1 element from FAQ occurring with this probability, then we combine 7 and 8 to fulfill this claim. Okay. Okay, so the assumption that E is of a coordinate from 0 could be extended such that E from 0 and X of length n, where X any value from FAQ except 0, then the consecutive element VP plus 1 such that VP satisfy 5, which is what is here, also exists. Okay. Yes, to generalize the previous construction, we give lemma 1, and this is as the following. So there are I blocks, and each has a length at most q minus 1 over 2. The encoder picks some z value and is equal VP plus 1 in FAQ in its corresponding ith block. So for example, here. Okay, to obtain some z vector such that has z0, z1. So z0 corresponding to the first block, z1 corresponding to the second one, and so on until 2k minus 1, 2 kappa minus 1. So there is at most this constraint in each block. Okay, which means there are at least 2 possible consecutive values similar to what we have achieved from before, but inside each block. Okay, and Z is not unique. The encoder first finds Z0 and in the 0th block and so on, and Z1, as you can see here in the second one, and so on. Then we can satisfy 5, and we will have output as the following, also except 0 and q minus 1. If we bring this H matrix and attach it to our construction 1 matrix G, so we will have G1H as our new matrix, and we get construction 2, so we can mask up to n cells. Okay, so we increase here. So from lemma 1, the encoder mask each block since that is mask all U up to n, and then it fulfills 5, and the rest of the proof for error correction follows construction 1. Okay. To reduce the redundancy, because we have 2 kappa here, then from previous, so we have our redundancy here. So the cardinality or the size of the code is n minus r minus 2 kappa. To reduce it to some other value we call L, which is at most 2 kappa, we have this condition on U, which is either at the minimum of both of these 2 values. And yes, so this is according to this lemma, we have this size of the block, lemma 1, following the proof of 8, theorem 8 in factors and Jacobi, we obtain the same. And in short, we have d minus 1 column of H. So this H here, we have d minus 1 are linearly independent, so as the d minus 2 column of H for sure. Since the encoder can mask these d minus 2 position as they can be set to any FAQ values. So now any u minus d plus 2, so the rest of the column of H, because labeled by u, can be masked assuming them without loss the last ith block with the size at most q minus 1 over 2 round down. Okay, floor down. So so H in this dimension L times n is seen as a special K of the H given in lemma 1, which is 2 kappa times n from lemma. Okay, and then we provide another construction of the reduced redundancy, and we have the same as our output. And then the coding model in construction 3 is n q n minus r minus L. So instead of minus 2 kappa and from construction 1 minus 1, we have minus L, and L is at most 2 kappa. So the worst case scenario, we need this redundancy. So by lemma 1, the encoder use H naught. We just give another name for the H here to be H naught. Okay, and for masking, and then the rest follow construction 2. Finally, we give a proposition of masking you by the error correction capable. So the encoder intentionally introduced, this is the proof, error in phi, setting, for example, to them to value 1. All phi location are masked are non-zero. Then if it has enough minimum distance as it's given here, which is this, then for sure C can correct both. Okay. And yeah, so to summarize, thank you. And if you have any questions.